So, what I want to discuss is another concept in information theory and statistics, which is very important. It's the Fischer Reformation. It's called the Fischer Reformation. So the way in which it is defined in statistics is that if you have a parametric model, is a probability distribution of a random variable x, might be real or discrete, then you can define what is called the score. The score is a random variable, and it is defined as the derivative with respect to theta of the log of f of x and theta, where this is a random variable which is distributed with this the same probability f of x and theta. So it's a random variable that depends on the probability distribution of x itself. Now let me discuss this problem for the case where x is a single parameter. Then we can generalize it to the case where x is a vector of parameters. Okay, so what are the properties of this score? Well, the first property is that the expected value of the score is equal to the integral in dx of f of x and theta times the derivative with respect to theta of the log of f of x and theta. So this is the integral in dx of f derivative with respect to theta of f of theta times 1 over f, right? And then this f cancel. So this derivative over theta, you can take it out. So this is the derivative with respect to theta of the integral in dx of f of x and theta, but this is equal to 1, okay? So the expected value of the score is equal to 0. So now the expected value of the score is equal to 0, and then we define the Fischer Reformation J of theta is defined as the variance of the score, which because the expected value of s is equal to 0, this is also the expected value of s squared. Okay, so and if you write it in full, this is the integral in dx f of x and theta times the derivative of times the score squared, which is log of f of x and theta all squared. Okay. So now there is another way of writing this the Fischer Reformation, which is if I take this integral, this is equal to the integral dx f the square of this. So I can write this as d theta log of f, and then I can make explicit one derivative with respect to, I can take one of the two derivatives with respect to theta, so this gives me 1 over f times the derivative with respect to theta of f. This cancel with this, and now I can evaluate this integral by parts. I can integrate by parts, which means that there is a minus sign and the derivative will go here. The term computed at the boundaries is equal to, will be equal to 0. So then this is equal to minus the integral dx of f of x and theta times the second derivative with respect to theta squared of the log of f of x and theta. Okay? So this is how the Fischer information is defined in the case for a single parameter. So if you have, let's see how this generalizes when you have a vector of parameters. So the generalization is straightforward. So if your theta is a d-dimensional vector, then you have you have that this theta can be written as say theta 1, theta d, and then the vector becomes the score becomes a vector. Okay, so because for each parameter theta a, you have a different score. And then again, the expected value of the score is equal to 0 because of the same argument as before. And then you define the Fischer information becomes a matrix because it's essentially the covariance of the SA and SB. It's the covariance of the score. It's the matrix of covariances of the scores. If you write it explicitly, then this is the integral in dx of f of x and theta times the derivative with respect to theta a of log of f of x and theta times the derivative with respect to theta b of the log of f of x and theta. Okay? So, and again, you can integrate it by part and write this in a more compact way as second derivative with respect to theta a and theta b of the log of f of x and theta. Okay, so this is the Fischer information matrix. So where does the Fischer information, why is this object important? Well, one important result that shows the relevance of the Fischer information is what is called the Kramer-Rao bound. So the problem is, so imagine that you have a sample x that is drawn IID from a certain parametric distribution f of x and theta. And now we want to estimate the parameter theta. So imagine that there is a an estimator, T of x, and yes, okay. So there is an estimator, so this is a function of the sample, and this is supposed to give you an estimate of the parameter theta. Okay, and let us suppose that T of x is unbiased, which means that the expected value of T of x is equal to theta. Okay, so that this is an expected value when all the x comes from this same distribution theta. Okay. Now, okay, so then camera bound is a very simple result that has to do with the variance of the estimator. Okay, it tells us that the variance of the estimator, now let's again consider the one-dimensional case. The variance of the estimator T of x must be cannot be smaller than 1 divided by n times the Fischer information. So essentially the Fischer information tells you what is the minimal value of the error of the variance that you can have, or of the error that you can have on your estimator. And so this tells you that estimators cannot have, say, arbitrarily small variance, but this variance is bounded by 1 over n times the Fischer information. The estimators that satisfy this inequality with the equality, so that for which this inequality is tight, are called efficient estimators. Okay, so when you have the equal sign, then T of x is called efficient. Okay, so what is how do we prove this relation? Well, this comes as a very simple proof. It comes from taking into account the covariance between the score and the estimator T. So what is this? Well, this is the expected value of S minus expected value of S times T minus expected value of T. Now, this is equal to 0. Then you have that this is the expected value of S times T minus the expected value of S times expected value of T, but then this is the expected value of S, which is 0. So this is just the expected value of S times T. Okay? Very good. Now, what I can do is also to use Cauchy-Schwarz inequality. So this will always be less or equal than the variance of S times the variance of T. This is because essentially Cauchy-Schwarz inequality tells you that so the integral of this will be less than the integral of this squared plus this squared. And I think there is 1/2, if I remember correctly. Okay? Very good. So now, then this is, or if you want, yes, so this is just the variance of the score is now if we are dealing with the sample x, then we should consider the variance, the score of this probability distribution. So the score is minus, is the derivative with respect to theta of the log of this. And so so this probability f is the product for I equal to 1 to n of the f of x of the xi and theta, where the xi are the components of your sample. And so you see that the score is the sum of I equal 1 to n is a sum of the score of the different random variables. So, and it's a simple exercise to see that then the variance of the score in this case is n times the Fischer Reformation. And why is this so? Because, well, if you take the expected value of this squared, then you can easily check that this is true because of this sum. Very good. So then this term is n times j of theta times the variance of 3/1/2. Okay. But so what is the expected value of s times t? So this is the integral from the integral on f of t of x times the derivative of the log of f of x and theta, right? This is just definition. So this is the integral in dx of f of x and theta times t times 1 over f times the derivative with respect to theta of f. Again, this 1 over f and this f cancel. So you see that this is the derivative with respect to theta that I can take out because nothing depends on theta here. So it's the derivative with respect to theta of the integral in dx of t of x times f. Okay, and well, this is an expected value on the whole sample. Okay, and okay, so what is this? Well, this is just the expected value of t, which is equal to theta. And so this is the derivative with respect to theta of theta. So this is just 1. So you see that what we have shown is that n times j times v is must be larger or equal to 1. Okay? So which is essentially the Kramer-Rao bound. Okay? Very good. So again, when theta is when theta is a vector, then the Fischer information becomes a matrix, and also you have you have a vector of estimators. Okay, so all of this generalizes, and what you find is that Kramer-Rao bound tells you that the covariance matrix between the estimators times the Fischer information matrix. So if you want, well, this should be J, A, B. So this is a so this is a positive definite matrix. Okay, so this times n. So this is must be larger or equal to this is a matrix which has all eigenvalues minus the identity. This is a positive definite matrix. Okay, or if you want minus delta AB. Okay, so yes, so the Fischer information gives you first principle bound on what error you can get on a parameter. What is the minimal error that you can get on a parameter? Okay. So there is so in order to understand better what is the role of Fischer information, so it is useful to think in general at the problem of parametric inference, or parameter inference. So what is this problem? So this problem is a problem where you have a space of samples. Here is where where the data lives. So each point is a sample of n observation of IID draws from a certain probability distribution. And then what you do when you do, say, maximum likelihood, then you associate to each of these points a point which is a point in the parameter space. Okay. Now the question that you can ask yourself is, based on this model, on the model, say, the model I'm using is f of x and theta. based on this model, can I distinguish two different samples? Okay, so if I take two different samples, two samples that are different, then these will correspond to two different points that if the samples are close enough, they will be close to one another. And the question is, when is it that I can say that these two samples come from the same distribution, or they come from a different distribution? So when is it that I can really distinguish these 2 points on the basis of a sample of n points? Okay, so you can address this question by using hypothesis testing. So it means that, say, if you consider these two hypotheses, that say x comes from f of x and theta, or hypothesis 2 that x comes from f of x and theta plus d theta, then what you can do is to fix an error epsilon, and you can ask what is the delta theta such that what is the delta theta such that I cannot distinguish these two hypotheses. Okay, so let's say that this error is the error is alpha, so is the error with which I accept this hypothesis if it is wrong, if the data really came from this distribution, and then I can compute beta, which is the error that I'm accepting hypothesis 1, but hypothesis 2 is really the right one. And if you remember, we estimated that in this situation where you fix the first type of error, then the second type of error is given by e to the minus n times the Kullback-Leibler divergence between the two distributions, between the distribution f of x and theta and the distribution f of x and theta plus delta theta. Okay, so now what I want to do is to find what is the delta theta that will make it so that this beta is also equal to epsilon, because this will tell me that if these two distribution, if these 2 points are closer than delta theta, then my second type of error will be I cannot essentially distinguish these two distributions. Okay, so in other words, 2 points that so at a precision epsilon, the delta theta that I get from here, imagine that I get a certain delta theta. So it tells me that all the points which are closer than delta theta cannot all the distribution that are closer than delta theta cannot actually be distinguished with this error. Okay, so what we have to compute is the DKL between two close by distributions, and this is the expected value of the log of this divided by this, but let me take a minus sign, so this is the expected value of f of x theta plus delta theta divided by f of x and theta. Now what I can do is to expand this numerator here. So this is the DKL in theta and theta plus delta theta is equal to minus this. So this is the expected value of the log. Here I substitute this by f of x and theta plus delta theta times the derivative with respect to theta. Let me write it in this way, of f of x and theta plus 1/2 delta theta squared times the second derivative of f. So if I take this by this, I get 1 plus 1 times delta theta over f times the derivative with respect to theta of f plus 1/2 delta theta squared divided by f, the second derivative with respect to theta of f, plus higher order terms. Okay, so and then what I can do is to expand further, to expand the log. So this is the expected value, so there is always a minus sign. This is minus expected value of first term is d theta. Well, this df is just d theta of log f. So this is just the score plus 1/2 delta theta squared over f times the second derivative of f. But you have another terms of order delta theta squared, which is when you expand this to second order, and this gives you minus 1/2 delta theta squared divided by f squared times d theta of f squared plus higher order terms. Okay. Now the expected value of this is the expected value of the score, which is 0. Now you can show that also the expected value of this must be 0. Okay, and I give you this as an exercise. So what you get is essentially the expected value of this, which is minus 1/2 with a minus is equal to a plus, which is 1/2 delta theta squared, and here you have the square of the score, which is essentially the variance of the score, which is the Fischer information. So what we get is that this thing is 1/2 times the Fischer information times delta theta squared plus higher order terms. And so what this tells you is that this error probability is equal to e to the minus n over 2 times the Fischer information times delta theta squared. Okay, this is for small delta theta. Okay, so then this tells you that well, there is a if you set this beta equal to epsilon, if this is the threshold probability or the error that you are willing to accept, then this tells you that the delta theta squared should be of the order of 2 over n times j of theta times the absolute value of the log of epsilon. Okay, so essentially all the points which have a delta theta, which is all the points which are closer than this delta theta, then for all these points the beta, the probability of error will be larger than epsilon, which means that these are not points that you can distinguish from one another. Okay, so this calculation extends in a very straightforward manner. If you have the theta is a d-dimensional vector, and what you find is that here you have the Fischer information times delta theta A times delta theta B. Okay? Or what this tells you is that essentially delta theta times J, or say, yes, the equation that you have is that delta theta A times J of AB of theta delta theta B somewhere A and B. This must be less or equal than 2 over n times absolute value of log of x. Okay? Now, graphically, in this plot here, if you have, if this is the point theta, so this equation here tells you that the delta theta around, so the equation that tells you what is the region of the parameters that you cannot distinguish from theta on the basis of a sample of n point and a precision epsilon is given by this equation. This equation is like an ellipsoid. Okay, so it's an equation like this one, where essentially these directions given by the eigenvectors of the matrix J, and the size of the axis of this ellipsoid are given by the square root, the inverse of the square root of the eigenvalues of J. Okay, so essentially this this calculation tells you that if you fix a certain precision epsilon, then this implies a discretization of your parameter space in terms of regions of indistinguishability. Okay, so this means that you can represent this your space of parameters as a coverage of different discrete points that essentially you cannot, which are the distributions that you can distinguish on the basis of a certain precision epsilon. So, the shape of this distribution, the shape of these indistinguishability regions is given by the Fischer Reformation. So, now the volume of one of these regions is given by the product of the different axes. Okay, so the volume of each of these regions will be proportional to 1 over essentially the product over the axis is the product of 1 over the square root of the length of the axis, that, as I told you, the square root the square root of the eigenvalues, 1 over the square root of the eigenvalues of J. And so if you want, say, if I write this in terms of eigenvalues, then this, so if I write delta theta lambda is the sum over A of delta theta A times, this is the lambda eigenvector of this matrix here, then you can rewrite this this equation here is a sum over lambda of delta theta lambda square times lambda. Okay, and your equation is this one. So so you see this tells you that in the space of eigenvectors that are the coordinates of the axis, then each, so this is an ellipsoid where the radius is 1 over the square root of lambda. So the volume of each of these regions is the product of this semi-axis. So it's 1 over, is the product over I of 1 over the square root of lambda I, which is essentially proportion, which is proportion 1 over the square root of the determinant of the matrix J of the Fischer Reformation computed in theta. Okay, So this tells you that, say, if you want to ask yourself how many different regions you have in a certain volume, okay, so you want to look at what is the number of indistinguishable, of distinguishable distribution that you have in a unit volume, then this will be proportional to 1 over the volume of just one of them. And so this will be proportional to the square root of the determinant of J. Okay, so so what this tells you is that so that different so if the determinant of J is large, then there are in a unit in a finite volume there will be many distinguishable models, many models that you can distinguish. Okay, so the if you think in terms of maximum entropy, you want to think that all these models that can be distinguished, they should have the same probability. Okay, so this tells you that if you want a maximally uninformative prior distribution over the parameters theta of this distribution, then this is the distribution that assigns the same probability to each of these volumes, okay, because this is a maximum entropy distribution. And so what this tells you that this probability distribution, the probability distribution over the parameter theta, should be proportional to the square root of the determinant of J of theta. So this is the idea behind these, say, uninformative priors. Which is also called as Jeffreys priors. And it is a prior where it's a prior on the parameter such that it is proportional to the square root of the determinant of the Fischer information. Okay? So this, if you want, encodes a state of maximal ignorance about the parameter theta of your parametric distribution here. Okay. Also, you can see that. So the Fischer information essentially gives you a geometric picture of the space of parameters, and indeed the Fischer information induces a metric on this space because it allows you to define distances between different points, and this idea of I mean, this geometric picture that you gain from this is what is called information geometry. So there is a whole field called information geometry that discusses the properties of space of parameters with a metric that is induced by the Fischer information. I'm not going to go into any detail, but I want to make a few examples of the Fischer information and on this uninformative prior. So, so let us take the simplest example of binomial variable. So is a variable such that f of x and theta is equal to theta to the x 1 minus theta to the 1 minus x, and x is either equal to 0 or to 1. Okay. So then the score is just the derivative with respect to theta of the log of f of x. So the derivative with respect to theta of the log of this, which is x times log of theta plus 1 minus x log of 1 minus theta. And so the score is just x divided by theta plus 1 minus x times divided by 1 minus theta with a minus sign. So it's minus 1 minus x divided by 1 minus theta. So if I simplify this, this is x times 1 minus theta minus 1 minus x times theta divided by theta times 1 minus theta. Okay, so this is the score, and actually you can simplify further because you see that here you have x times theta with a minus sign, here you have x times theta with a plus sign. So the score is actually x minus theta divided by theta 1 minus theta. Okay. Indeed, you see very clearly that because the expected value of x under this distribution is equal to theta, then the expected value of the score is equal to 0. And what is the Fischer information? The Fischer information is just the expected value of the score squared, so it's x minus theta squared divided by theta squared 1 minus theta squared. But the expected value of x minus theta squared is just the variance of x, which is theta times 1 minus theta. So this is just 1 divided by theta 1 minus theta. Okay? So now if you look at this, as a function of theta between 0 and 1, so the j has this form equal to this, right? Which is diverges at 0 and 1. So the Jeffreys prior of this distribution would be just a constant divided by square root of theta 1 minus theta, and this constant is just the normalization is given by beta function, so this is just 1 over pi times 1 divided by square root theta times 1 minus theta. Okay? If you work it out, it should be 1 over pi. Okay, so you see that also this prior distribution gives, would be something like this. And it would give a lot of probability to theta close to 0 or theta close to 1, and not so much probability to theta equal to 1/2. So why is this so? So if you think about it, if I tell you, imagine that I show you a sample of many, a sample X of many draws from this random variable, and I tell you that 1 over n times the sum over I over xi, the frequency of ones, is very small. Okay, so it's close to 0. Okay. Then, if this is true, then your precision with which you can estimate theta is also very small, because you know that theta will be very close to 0. Okay, so in this sense, in this region here, you can distinguish more distribution, because your error on theta is much smaller. Instead, if you are close to 1/2, then the fluctuations of this sum are much larger, and this means that you cannot really distinguish very close points. Okay, just because, let's say, when you generate data from one of these points, the data that you generate from one point and a nearby point is essentially undistinguishable. Okay, and so this is a little bit the intuition about this, the Fischer Reformation. And so there is another observation that I want to make about the Fischer Reformation. And now let us consider exponential families. Okay, so distribution where f of x and theta is equal to as this form. Okay, e to the theta times some function of x minus some. So this is just the normalization. Is a function which gives you the normalization. Okay. Then the score for this distribution is just the derivative with respect to theta of the log of this. When I take the derivative, I just get tau of x minus the derivative of phi with respect to theta. But the derivative of phi with respect to theta, as we have seen, is just the expected value of tau. Okay, so this is just tau of x minus the expected value over the same distribution theta of tau. So it is clear that the expected value of S is equal to 0. And now if you, the Fischer information here, the Fischer information is just the variance of the score, which is the square of this, which is also equal to the variance of tau of x. Okay, and but this is also related to the second derivative of phi with respect to theta squared. Okay, so the and what is this? Well, you can also define this as the derivative of the expected value of tau of x with respect to the parameter. Okay. Very good. So, what is this? Well, this tells you how much the behavior of your model changes, or the observable of your model change, if you change a little bit the parameters. Okay? So this is, in the language of statistical physics, this is a susceptibility, as we have seen. No, this is a susceptibility. It is very large when the parameter of when the behavior, the observables change a lot when you change a little bit the parameters. Okay. Now in statistics, instead, this object here is the data, and and these are the parameters. Okay, so the Fischer information, if you want, tells you essentially how much the data changes when you change the parameters. Okay, so what you want in statistics is that when you change a little bit your data, imagine that you estimate a parameter, and on the basis of some data, now you add some more data, so you change a little bit the data. What is really idea is that your parameters do not change much when you change a little bit the data. So these are models that generalize well, in the sense that your estimate of the parameters does not change completely when you add some more data. Okay, so generalization, the fact that your model generalizes well means that this object here must be very, very large. Okay, or if you want that the change in the parameters induced by changing the data is very small. Okay. Now, so for example, this is clear if you look at the picture before on the binomial variable. It is clear that if you are between if your parameter is close to 1/2, then when you change a little bit your parameters, your data do not change much. Okay, because it's essentially, if you change, say, in this case, the probability of having of success from 0.5 to 0.51, then it does not really change. But if your probability is 0.01 and you change it to 0.02, then your data changes a lot. Okay, so this is essentially the measured by the Fischer Reformation. Okay. The interesting thing is that you see that when you look at the problem in statistics, you would like to have models that when you fit them, they have a large susceptibility. Okay, a large susceptibility, if you think at the same model in the statistical physics perspective, means that you want models that are close to a critical point where the fluctuations are very large. And indeed, say you can see this connection if I ask you the following question. So imagine that you want to estimate, you want to say look at the system and estimate its temperature. And imagine that this system is just water. And imagine that when you look at this system, you just see water which is liquid, okay, which is in a liquid phase, like in a glass of water. Then when your estimate of the temperature will be anything between say 0 degrees and 100 degrees. I mean, your uncertainty on how you estimate the temperature is very large. But if your system is close to a phase transition, so if you observe in water that there are some bubbles of vapor, then your estimation of the temperature is very precise, because if you have an idea of what is the pressure, then you can be very precise in estimating the temperature. So this a little bit tells you that, say, because at the critical point, if you change a little bit, if you change your temperature of water, say just a few degrees below or above the boiling point, then the behavior of water changes completely. Okay, and it's only at the critical point that you have this very specific behavior, and this is what allows you to estimate parameters very precisely.